So topic number 21, reversible reactions and equilibria. We are going to discuss specifically reversible reactions in detail and also what dynamic equilibrium is about. Starting with, first of all, reversibility. Now, in case of taking an example for reversible reactions, we usually go with dehydration of copper to sulfate crystals. This is easiest of the examples, and that can easily be performed in lab too. Now, if you heat blue copper to crystals of this formula given over here, the blue crystals turn to white powder. Water is driven off in the form of steam. Heating causes the crystals to lose their water of crystallization, and white anhydrous copper to sulfate is formed. I hope you remember water crystallization from Unit 2. Now, the white salt is formed, which is USO4. We specifically call it anhydrous. Anhydrous means without water. Now, heat is needed for this reaction to occur. This is a dehydration reaction. Since this is a dehydration reaction and heat is required for this reaction to occur, you would automatically understand that this reaction is an endothermic reaction. Make sense?
Yes.
Okay. So if you add water to the white solid, if you try to reverse this entire thing, it turns blue again. It also becomes very warm, so much so that the water is capable of turning the incoming water into steam as well. Since a lot of heat is released from this reaction, this hint gives us the idea that this is an exothermic reaction. By the way, let me clarify, this is a hydration reaction since we are adding water to it. When we were removing water, we're calling it dehydration. When we are adding water, this is known as hydration reaction. The original change has been exactly reversed. We converted blue salt to white, and then we reconverted the white salt back to blue. Even the heat that you put originally has been given out again. This is called a reversible reaction. It is indicated by a special arrow. We call that fish hook arrows. Since these kind of arrows are used for fishing purposes, we call them fish hook arrows. Fish hook arrows means the reaction can go in the forward direction as well as in the reverse direction. All right. So moving on. Second example, heating ammonium chloride. Ammonium chloride, the white crystals disappear from the bottom of the tube and reappear further up. Heating ammonium chloride splits it into colorless gases, ammonia and hydrogen chloride, and we can reverse the entire process. Now, we have white solid, which is NH4Cl, ammonium chloride. It is converted into two colorless gases. Heat is needed for this reaction to occur, endothermic, right? And these gases recombine further up the tube where it is cooler to form the white solid again. So we get the white solid on the top of the tube. So heat is released from this reaction. It's exothermic. So we can reverse the changes. Now, the reaction between acid and a base like this has been discussed before. This reaction is also considered as an example of thermal decomposition. Since all thermal decomposition reactions are endothermic, this one is also endothermic. If you add water to the white solid, it turns blue again. It also becomes very warm. We also understand those facts about the previous example. So I guess it's pretty understandable that how this reversible arrow is shown in this reaction. If it all makes sense, let's move on, shall we?
Yes.
Good. So moving on, reversible reactions in a sealed container. A sealed container means that no substances are added to the reaction mixture and no substances can escape from it either. On the other hand, heat may be either given off or absorbed. So heat can make its changes, temperature can make its changes, but not the substances. Imagine a substance that can exist in two forms, one of which will represent by blue squares and the other one by yellow squares. Suppose you start off with a sample which is entirely blue. And after a short time, some of the blue squares have turned into yellow ones. Because you're starting with a higher concentration of blue squares at the beginning of the reaction, the rate at which they turn yellow will be relatively high in terms of number of squares changing color per second. The number of blue squares changing color per second, the rate of change will fall as the blue gradually gets used up, which is pretty much the thing we covered in the last topic. We do understand the reaction is fastest at the start, and slowly, since the reactants are being consumed up, the reaction slowly falls off on its rate and gets slower and slower. And there comes a time when it's almost dead. Now, moving on with this example, the yellow squares can also change back to blue once again. Now, this is because it's a reversible reaction in which the products can react with each other and go back to form reactants. At the start, there aren't any yellow squares, so the rate of change from yellow to blue is 0. As the number increases, the rate at which yellow changes back to blue also increases. And the key point here is this. Imagine you started off with 64 blue squares, which is the case over here. If you notice, these are 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. So actually we have 64 blue squares. There was 1 in a 4 chance of each of them changing color. So in the first second, only 1 out of 4, which means 64 divided by 4 is equal to 16, would change color, leaving 48 blue squares. In the next second, a quarter of these change color, but that's only 12. This leaves 36 blue ones. In the third second, 9 would change color, and so on. The rate of change falls as the concentration of blue square falls. Now, this should make much more sense if we relate it to the previous topic of yesterday, that first you'll see 16 blue ones changing, then you'll see 12 blue ones changing, then you'll see 9 blue ones changing, so on and so forth. So this number would fall every time there is a change. Moving on, further elaborating. Now, if we make a graph for it, we do understand that according to time, if the rate of blue to yellow falls per unit time, the rate of yellow to blue also increases per unit time. There comes a time when both the rates become equal, and we call that equal point as equilibrium. Means the rate of forward reaction and the rate of reverse reaction becomes equal. Means the number of blue squares changing to yellow and the number of yellow squares changing back to blue becomes equal. So at that time, blue squares are changing into yellow ones at exactly the same rate as yellow ones are turning to blue. Supposedly, let's say 3 blocks turn from blue to yellow, and at the same time, 3 yellow blocks will turn back to blue, will give us the idea that they both are converting at the same rate. All right. So what would you see in the reaction mixture when it happens? The total number of blue and yellow squares would remain constant, but the reaction would still be happening. If you followed the fate of one particular square, sometimes it would be blue and sometimes yellow, since it would keep on changing. Since blue will change into yellows and yellows will change back into blue, so the rate at which both of these reactions will be the same, we call that point equilibrium point. From a third-party observation, it sometimes seems that nothing is happening. Actually, that's not true. Change is happening, but both the changes are occurring at the same rate, so it seems like nothing's happening. All right? We call this example as a dynamic equilibrium. Does that make any sense? Or should I need to come up with some funny example?
That makes sense.
It makes sense? Good. Okay. So it is dynamic in the sense since the reactions are still continuing, but the rate of forward reaction is equal to the rate of reverse reaction. We call that equilibrium. It is in a sense that the total amounts or concentration of various things present, in our case, reactants and products, is now constant. So it gives us the idea that equilibrium is the point where the formation of reactants from the products or formation of products from the reactants is at an equal rate. And their concentrations do not change. But the change or the conversion of reactants into products or products into reactants keep happening. This gives us a pretty good idea about this dynamic equilibrium. Let me tell you, if there was no change happening, we wouldn't call it a dynamic equilibrium. I hope that in physics, you might have studied another kind of equilibrium, and that is static equilibrium. That is when no change is happening. Everything is at rest. But in chemistry, unfortunately, static equilibrium is only hypothetical. Nothing, it is rest. So the products are changing into reactants, the reactants are changing into products. So we can't have the concept of static equilibrium. We can only have the concept of dynamic equilibrium. Notice that you can set up a dynamic equilibrium only if the system is closed in a sealed container. That's where the sealed container parts kicks in. If, for example, you remove the yellow squares, as soon as they're formed, they would never get the chance to turn back to blue again. So what was a reversible reaction would now go entirely in one direction as blue square turns yellow without being replaced. Now, I give this as an example of naughty siblings going to fishing. Are you the only child, or do you have some siblings?
I have a brother.
I have a brother. Let's, for my example, assume that your brother is very naughty. You and your brother go to fishing. Let's assume that you are the elder one. So you take the responsibility of fishing and you ask your brother to just sit with you. And let's say you are fishing and you have a net and then you have a basket and your brother is sitting alongside you. Let's say this is B, this is you, this is your brother, all right? And you start up fishing, you're very lucky, you get a fish and then another one and another one, and it goes on and you have 8 fish. You keep on fishing, you are being a little bit greedy and you want to catch as many fish as you can since you're going to then have a party. All right. So you catch another fish and you put it in the basket. Now you have 9 fish. Your brother, who is just sitting and watching and tired of being idle and is not getting the fishing hook anymore, comes up with a mischievous plan. He starts putting the fish back into the pond. Now, the rate at which you catch one fish, he's a little bit impatient and he puts 2 fish back into the stream again. You would notice after some time, even when you're still able to, lucky enough to catch more fish, the basket is going shorter on fishes since your brother is slipping those fishes quietly back into the pond without you having to notice him. You would notice there would come a time that you're still catching fish and you are under the impression that you probably have reached a dozen fish in the basket, but turns out when you reach home, you don't have a single fish in the basket. Now, you are a forward reaction, getting that fish, putting to the basket. Your brother is the mischievous reverse reaction who is taking the fish and putting them back into the stream. All right. So there would come a time that your rate of catching fish and your brother's rate of throwing the fish back into the river becomes same. You would end up having no fish in the basket when you return home that evening. Make sense?
Yes.
Now, you cannot say the entire thing was static. You never caught any fish, right? You would always fight with your brother that I caught some fish and I am the witness to it. Even when the basket's empty, your brother cannot argue with you that you never caught any fish, right? So there was some action. There was some action on your side. You caught the fish and you're going to fight with your brother. At least you're going to argue that the basket was never empty because I tried to fill the basket as much as I could. So since you are the witness that you caught fish, you would always argue, and your brother must be slipping the fish back into the water. So there was action on your side and a reaction on his. We can't call it a static equilibrium. This was a dynamic equilibrium. But the rate at which you were catching the fish and he was slipping the fish back into the water, it was same. Make sense?
Yes.
And at the end of this whole thing, I hope you understand that what is dynamic equilibrium and would not to the conclusion that your brother needs a beating, right? All right. So moving on, that was just a funny example to make sure that you understand there is some action. It's not static, and the forward and the reverse reaction can be at the same rate. Now, consider the reversible reaction that occurs when calcium carbonate decomposes. Calcium carbonate, when decomposes, forms calcium oxide and carbon dioxide. One of them is solid, one of them is gas. If we are not doing it in a closed container, then we're allowing the gas to escape the system. Carbon dioxide, in this case, reverse reaction would not occur. Carbon dioxide gas will keep leaving the system, and instead of writing this equation like this, we should be writing this equation like this. So for an open container, this kind of equation. For a closed container, the equation should be written with a reversible arrow. Make sense?
Yes.
Great. If that makes sense, let's clarify the position of equilibrium. Taking a general case where A reacts reversibly to give B. The reaction from A to B, left to right reaction, is described as the forward reaction. The reaction from B to A, right to left reaction, is described as the reverse reaction. Let's clarify that. If we let this reaction come to an equilibrium, then measure the amount of each substance present, we might find that we have 90% of A and only 10% of B. Because there is more A than B present at the equilibrium, we can say that position of equilibrium lies to the left. It is important that equilibrium does not mean 50% of reactants and products, which is the most common assumption student comes up with. No, that's not right. Okay, I was saying there was a little bit of lag with my internet. I was saying most of the time students try to assume that equilibrium means that there would be 50% of reactants and 50% of products. That is not true. The key thing is that the concentration of A and B will stay constant at equilibrium no matter what the concentrations are. The concentrations can be 90 and 10, 80 and 20, 70 and 30, 1 and 99, 50 and 50. It can be anything. You don't have to hard and fast put up a rule that it is supposed to be this percentage. All right. These concentrations will remain constant until we change the conditions. For instance, we can change the temperature of the system. We can change the pressure of the system. If we increase the temperature and allow the reaction time to reach equilibrium again, we might find that this is now 80% of A and 20% of B. So there was more of forward reaction than there was reverse reaction. Because the change we made decreased the concentration of what is on left, which we are calling A, and increased the concentration on the right-hand side, which we're calling B, the position of equilibrium has shifted to the right. It does not matter, we still have more A than B. We're looking at how things change when we change the conditions. This is a very important part, and I hope you understand it. If you don't, let's do it in some other way. Do you understand this?
Yes.
Good, good. So don't always consider and try coming up with the judgment of which of these have a higher concentration. It's not about that. It's about the fact that when we change the conditions, what is the change after the changing of conditions? Is the equilibrium shifting towards right and forming more products? Remember, when I use the term of equilibrium shifting to right, it means it's forming more products. When I'm using the term equilibrium shifted to left, it means it's making more reactants. In this case, it shifted to right. It means it increased the amount of products than they initially were. It might be the other way around. It might break down some more products and give me some more reactants. In that case, we would use the phrase equilibrium has shifted to the left. Make sense?
Yes.
Great. If it does, then the rest of this chapter is pretty easy. Let's come to the fact that we can change the conditions and we can affect the position of equilibrium. Now, let's discuss that. When the conditions of a system in a dynamic equilibrium are changed, let's say temperature or pressure or any other changes, it may be concentration of reactants, it may be concentration of products, it may be adding a catalyst. We have considered like 4 to 5 different sets of conditions in the previous topic, right? So when we do that, the position of equilibrium might shift. Now, the equilibrium can only shift in 2 directions, either left towards the reactants or right towards the products. But however, we are always going to discuss it in terms of products because to be very frank, in industry, we are looking at the products. We're not looking at the reactants. All right. So a useful way to help you decide what happens if various conditions are changed is to remember that the direction always set about counteracting any change you make. This is similar to the idea if the room is too warm, you might take off your jacket so that you can cool down. If the room is too cold, you might put some more clothes on in order to get warm. So this is the influence of the reaction for the changes that we make. All right. We can change the pressure, we can change the temperature, we can add a catalyst, we may change the concentration of reactants and products. This can change the position of the equilibrium. However, in fact, adding a catalyst turns out to have no effect on the position of equilibrium. Okay, just a second, I'll be right back. Okay, so let's start with changing the pressure. Now, remember, solids and liquids are not affected by pressure. So I was saying solid and liquid. So I was saying that changing the pressure is something that will not affect liquids and solids. All right, this can only affect gases. So when we are talking about pressure, we usually consider the equations that are made up of gases. Consider in this example, A, B, C, and D are all gases. So this really applies to a reaction in which at least one of the reactants or products is a gas, where the total number of gaseous molecules on both sides of the equation are different. Now, how is that? How does that work for us? Now, 1 mole of 1, 2 moles of B, 1 mole of C, 1 mole of D. So we have overall 1 plus 2 is equal to 3 moles of reactants. We have 1 plus 1 is equal to 2 moles of products. So we have different number of moles of products on left and right. Make sense?
Yes.
So pressure is caused by molecules hitting the walls of the container or the lid of the container. If you have fewer molecules in the same volume at the same temperature, you have a lower pressure, which means we have a lower pressure on the product side, we have a higher pressure on the reactant side. What can we do about it? Let's see it on the next page. Now, if you increase the pressure, the reaction will respond by reducing it again. It can reduce the pressure by producing fewer gas molecules to hit the wall of the container. In this case, what would it do? It would produce product molecules. Since product molecules have lesser number of molecules increasing the pressure will cause the position of equilibrium to always shift in the direction where it produces smaller number of gaseous molecules. In this case, the equilibrium will shift towards the right. Make sense?
Yes.
Good, good. So let me clarify. By taking this example, 1 mole of nitrogen reacts with 3 moles of hydrogen and forms 2 moles of ammonia. On the reactant side, you have a total of 4 moles. On the product side, you have a total of 2 moles. So there are a high number of molecules or moles over here and a lower number of molecules or moles on the right-hand side. If we increase the pressure, the reaction should shift towards the right in terms of position of equilibrium. Why? Because we have less number of molecules over there. Increasing the pressure will cause the position of equilibrium to shift in the direction which produces a smaller number of gaseous molecules. Make sense?
Yes.
Good. Now, what happens if we have something different? What happens if we have same number of gaseous molecules on both sides? Let's consider this example. 1 molecule of hydrogen reacts with 1 molecule of iodine, which is 1 plus 1 is equal to 2, to give us 2 molecules of hydrogen iodide gas, which is 2. So in case of 2 versus 2, increasing the pressure or decreasing the pressure would make no effect. Neither the position of equilibrium will shift towards right, nor it shift towards left. It does not affect the equilibrium. Make sense?
Yes.
Good. Let's take another example, which is not the part of the book, but I want to make sure that you understand all 3 scenarios. Third scenario. We have a gaseous reaction in which sulfur trioxide is being decomposed into sulfur dioxide and oxygen. And since all 3 of them are gases, we can easily change pressure to affect the equilibrium. Now, we have 2 molecules on the left side and 2 plus 1 on the right-hand side, which is equal to 3. Since we have a lower number on the left and a higher number at the right, increasing the pressure would take the equilibrium towards the left, towards the reactant side. So it would produce more reactants. Make sense? So in order to summarize, increasing pressure, the position of equilibrium shifts to the sides where it has fewer gas molecules. Decreasing pressure, the position of equilibrium shifts to the sides where it has more gas molecules. All right. So in this equation, we should really go with lower pressure. We should decrease the pressure in order to take it towards the product side. All right. Make sense? Can we move on?
Yes.
All right, great. So next effect, changing the temperature. Now, in case of temperature, delta H is the value we should be interested in. Delta H is the value which tells us whether the reaction is exothermic or endothermic. If you remember from our previous topics, you would notice that if the delta H was negative, it gave us the idea that the reaction was exothermic. And if it was positive, it gave us the idea that it was endothermic. Now, for a reversible reaction, if it is quoted like this, there is one thing we need to understand. And that is, for a reversible reaction, if delta H is quoted as negative, it means the forward reaction is exothermic and the reverse is endothermic. What I'm trying to say is that delta H quoted for a reversible reaction is always for the forward reaction and not for the reverse one. and the reverse one would be exactly the opposite. Make sense?
Yes.
Great. If it does make sense, you would understand that in this example of A plus 2B giving us C plus D is that the forward reaction is exothermic and the reverse reaction is endothermic. And the delta H value is exactly the same amount for forward or reverse reaction. Now, moving on, suppose you change the conditions by decreasing the temperature of the equilibrium. For example, the reaction was originally in equilibrium at 500 degrees centigrade, and you lower the temperature to 100 degrees centigrade. The reaction will respond in a way that increases the temperature again. How can it do that? Now, let's understand. If some A and B are converted into C and D, more heat is given out because this is an exothermic change. The extra heat that is produced will warm the reaction mixture up again. In other words, decreasing the temperature will cause the position of the equilibrium to move to the right-hand side and more C and D would be formed. Let me make some sense out of it by saying it in a simple way. If you try to decrease the temperature, the system will behave exactly in the opposite way. It will try to increase the temperature. The system can increase the temperature by going in the direction of exothermic reaction. So let's take the example again. If the reaction was occurring at 500 degrees centigrade and we reduced it down to 100 degrees centigrade, the system would try to go in the direction of exothermic reaction. And this is the direction of exothermic reaction. So the system is actually shifting towards right. And in that way, it would produce more heat. It would heat up the system and would try to bring the temperature up back again as much as it can. Make sense?
Yes.
Good, good. Let's say if it was 500 degrees centigrade and we increased it up to 750 degrees centigrade, what would the system do? System would instead follow the path for endothermic change. And this time it would go for an equilibrium shifted towards the left. It would break down some products, form some reactants, try to cool the system down and turn the temperature back down as much as it can. Make sense?
Yes.
Good, good. Then you do understand the system is like the naughty child who is trying to do exactly the opposite of what he's told. Let's consider this system is like your younger brother. I don't know whether he's naughty enough or not, but let's for now assume the system is behaving like a naughty younger sibling. All right? That way you might remember it till exams or till tests that how the system behaves. So getting back to the example, A plus 2B was 80% and C plus 2D was 20% at 500 degrees centigrade. At 100 degrees centigrade, this is 60 and 40. So increasing the temperature will have exactly the opposite effect. The reaction equilibrium will change to remove the extra heat by absorbing it in an endothermic change. This time the reverse reaction is favored, just like I explained. So the position of equilibrium moves to the left. So there are two key points that are important. At equilibrium, the rate of forward reaction is equal to the rate of reverse reaction. So as much heat is being given out as taken in, so nothing appears to change. So for these kind of reactions, the forward and reverse are actually exactly opposite, and the exact kind of temperature changes are there. So as a third party observation and an outside observer, we might seem or find like nothing is going on. Actually, the changes are going on, but since there is no change in temperature, we don't find a change in heat as well. Now, in an endothermic reaction, the heat is converted to a different form, chemical energy, so it is being removed. All right. So to summarize, increasing temperature, the position of equilibrium shifts in the endothermic direction. Decreasing temperature, the position of equilibrium shifts in the exothermic direction. I hope that makes sense.
Yeah.
Good. And the third fact, we previously discussed that adding a catalyst actually does not changes the position of equilibrium. So what does it exactly do? Let's define it in just a few lines. Adding a catalyst speeds up reaction. In a reversible change, it speeds up forward reaction. It speeds up reverse reaction by the same proportion. So for example, if it speeds up the forward reaction 10 times, it speeds up the reverse reaction 10 times as well. So the net effect, there is no change in position of equilibrium if you add a catalyst. The catalyst is added to increase the rate at which equilibrium is reached. So it means less time to reach equilibrium. That's it. That's the only thing we want when we add a catalyst. Why? Because time is a very important commodity. And frankly speaking, if lesser time is taken for some task, it is usually taken as a blessing. Imagine you have your homework to do, and your homework requires 3 hours for you to sit and do your work. And imagine one day something magical happens and that homework starts taking an hour instead of three. Wouldn't that be a blessing? Now you have 2 hours free to yourself. Sounds a very good magic. Every child on the planet should have this magic. I don't know whether you get 3 hours homework or not, but definitely every child would wish to have this kind of magic. All right, moving on. So an example to illustrate how changing reaction conditions can affect the position of equilibrium in a reaction. Now, nitrogen dioxide is a dark brown poisonous gas. It can join together in pairs. We call that dimerize to make molecules of dinitrogen tetroxide, which is N2O4, which is colorless. So one of the gases is brown, one of them is colorless. There is a dynamic equilibrium between the two forms. The forward reaction from the brown gas to the colorless gas is exothermic at minus 57 kilojoules per mole. What would happen if we change the factors for this specific reaction? Let's consider one by one all the factors. The effect of pressure. It's pretty simple. We have two molecules on one side, one on the other side. What would happen if we increase the pressure? Would the equilibrium shift towards right or left? What do you say?
Right.
Perfect. It shifts to right. Why? Because there are fewer gas molecules over there. Make sense?
Yes.
And if I lower the pressure, vice versa would happen. It would shift towards the left because this time it would try to shift in the favor of higher number of molecules. All right. So there is one very important info over here. You have to be very careful here about predicting exactly what color changes do you see. If you increase the pressure, for example, you squeeze the same number of molecules in a smaller space, so the color will darken initially. Then it fades a bit as the equilibrium reestablishes, but not to its original color. The gases are still compressed. So this is something very important. I hope that makes sense. Does it?
Yes.
Great. So moving on. Effect of temperature. Since this equation showed you that the forward reaction was exothermic, what if I increase the temperature? In which direction would the position of equilibrium shift to? Right or left? Increasing the temperature.
Right.
Actually left. Okay. So why? Since, let me clarify, the forward reaction is shown with a negative, so it's exo, and the reverse reaction must be endothermic then. Increasing the temperature would take it in the direction of endothermic reaction. Decreasing the temperature takes it in the favor of exothermic reaction. So decreasing the temperature would shift the position of equilibrium towards right, and increasing the temperature would shift the position of equilibrium towards left. Make sense?
Yes.
Great. Now, oh, wait, I've got one important thing. So if you're decreasing the temperature and the position of equilibrium is shifting towards right, then there will be more dinitrogen tetroxide, and the color of reaction mixture will start to fade since it's colorless. Now, if we increase the temperature and we're shifting it towards the left, then more nitrogen dioxide would form and the color of gases will start to darken since it's brown. I hope that makes sense too.
Yeah.
Now, you can see this happening in figure 21.8, and you would see 3 test tubes containing this equilibrium mixture. One is at lab temperature, one is at an ice, one is at an hot water. Notice that the hot one is very dark brown, probably NO2, contains a high proportion of NO2. The one that is in the ice is slightly paler than the one that is in air, showing the one that is paler has a greater proportion of dinitrogen tetroxide, and the one that is in the center is probably at equilibrium in between both. Make sense? So that's why
Yes.
we use the terms darken the color or fade in the color or terms like that. Since it does not become exactly colorless or exactly dark brown, that's why we use to choose the words like this. Choose to use the words like this, my bad. Okay, so the effect of concentration, something that we still need to do. Changing the concentration of reactants or products in a reversible reaction also has an effect on position of equilibrium. Remember, whatever kind of change you're going to make, the system will behave or react like a naughty younger sibling. It is always going to cause the change. Let's say a reaction is occurring for A plus 2B giving us C plus D. If you add more A, the system will quickly consume that A, form some more products, and removes the extra A that you added to the system. So the equilibrium shifted towards the right. Let's say you remove some C. System will try to oppose the change. It would quickly take some A and B, react them together, produce some C, and try to replace the change as much as it could. So what happened is that the reaction again shifted towards right. Make sense?
Yes.
In order to make more sense, let me clarify. If you're adding a reactant, if you're removing a reactant, if you're adding a product, if you're removing the product, I am going to put them as forward or reverse reactions. So adding the reactant or removing the product always takes the reaction into forward direction. Removing the reactant or adding a product will take the reaction in reverse direction, or right or left equilibriums, position of equilibriums. So this is a pretty easy way to remember these 4 possible scenarios. Since the examiner may ask you to add a reactant or to remove a reactant or to add a product or to remove a product, I think you should note them down. And when you're done, let me know. And this also finishes the chapter.